everyone. Today we're going to look at the forces that shape our Earth. In other words, what makes the surface of the Earth look the way that it does? As we're working our way through this lesson, think about the topography of our planet. What causes the mountains, the valleys, the volcanoes, the trenches? You should all have a chart to fill in as we're working through this lesson. Remember, you can always pause to fill in answers or to go back to double check. At the end of class, you should be completed with the chart, and you'll need to make sure you turn it in. To understand what's happening on the outside of our Earth, we need to look on the inside of our Earth. So let's take a look at the different layers that can be found inside of the Earth. In the very center is the layer called the inner core, and it is a huge metal ball made of iron. And it is extremely hot, but it is solid. And then the next layer is called the outer core. The outer core is mostly liquid, and it is made of iron and nickel. Then the mantle is the thickest of all of the layers, and we can really divide the mantle into two different parts. The lower mantle, which is the one that would be closest to the outer core, is a solid rock. And the rock is hot enough to melt, but because it's solid, the pressure is pushing down on it. The upper mantle, then, what's closer to the crust, is made up of liquids and solid. The lower part of the upper mantle has quite a bit of liquid in it, while the upper part, or the upper region of the mantle, is more stiff because it's not as hot. And so the part that is liquid, you could say that it's moving at a very slow pace, about the same pace as the time it takes for your fingernail to grow. Then the final layer is the crust. The crust is what we live on, and there's crust on the land that we live on, and there's crust under the ocean. And it varies in thickness. Some part is not that thick, maybe less than a mile, while some parts of the layer are up to 3 miles thick. On our crust, we have what we would call tectonic plates. And as you look at the image here, you can see it almost looks like a puzzle. Where the red lines are, that is what is dividing the area, the land, the pieces. And this is where you're most commonly going to see earthquakes and volcanoes. But the tectonic plates, why are they moving? What's causing that? Well, it's because, remember, we just talked about the inside of the Earth, and we were talking about the mantle. And remember, the mantle layer, part of it is made of liquid, and so liquid moves. And the crust on top of that liquid is going to break apart at times or push together. It's going to move with that liquid. And it's a very slow movement. And that's why you guys may remember last year when you learned about Pangea, which was basically just one landmass. And over millions of years, the landmass broke apart into what we know today as our 7 continents. But it's a very slow process of the moving of the tectonic plates. As you can see from this diagram illustrating how the Earth's crust is layered over the mantle, and the mantle, remember, we learned about, was not completely solid. There are places where it's hot and liquid, and it is continuously flowing as it gets closer to the surface, to the crust. It cools down, but then it circulates back down and warms up again and follows that same process. In the next slide, you're going to be watching a video, and if you were not able to get the first question done, what are the 4 layers of Earth and what causes the plates to move, you can also find the answer on that video.
Flying past the Earth at this time, we see a vast gray ocean beneath a red-tinted sky, punctuated by volcanoes and small land masses. And unlikely as it seems, life may have gained a foothold already. That life in the oceans that gave birth to it may actually be vaporized many times by cataclysmic bombardments, which have slowed but not yet stopped. Earth has begun to take on its final form, a crust, a skin so thin it would be less than a sheet of paper were the Earth the size of a basketball. And under that, a molten semi-solid mantle that boils in extreme slow motion. And finally, two cores, a liquid iron core pulsing out a magnetic field that helps shield us from a deadly cosmic wind from our sun. And a solid nickel and iron inner core. By now, the remarkable process of plate tectonics has kicked into gear. Though how and when it started exactly, we do not know. For what follows next, you might want to strap yourself in. It's going to be a bumpy ride. Here's how it might have happened. At first, Cretans and one continent called had the planet all to themselves. Then, around 500 million years later, Arctica took shape. About another 500 million years passed before Atlantica formed. The continents roamed separately until, about 1.8 billion years ago, Arctica collided with what is now Eastern Antarctica to form Nina. Then Nina, Atlantica, and collided 1 billion years ago, forming the supercontinent Rodinia. After about 300 million years, the three landmasses separated and came back together in a new configuration, Pangaea. Pangaea came apart too. When Pangaea split, and Atlantica split up too. If you're confused, join the club. Even the Earth seems confused. All of this movement made for a host of unlikely neighbors way back when. North America's eastern seaboard once rubbed shoulders with Chile. California and Australia were neighbors, if not connected. And Brazil was either connected to Nigeria or very close. Run the Earth time machine backwards, and you can see why. But no matter how many times you run the demolition derby of the continents, a question remains. What the hell is driving them? Hell, apparently. The force driving the plates is the slow movement of the super-hot semi-solid mantle that lies below the rigid plates. Like hot soup, magma boils in slow motion. Superheated magma rises to the surface, begins to cool, and then sinks back down to the bottom of the pot, where it is reheated and rises again. This cycle is repeated over and over to generate what scientists call a convection cell, or convective flow. But where's the heat source keeping our earthy soup performing its circular gymnastics? Well, most of it is left over from the spectacularly energetic collisions and gravitational crushing that created the Earth to begin with. It's still trapped down there, and it wants it out. And there's something else in the molten depths that makes it pretty hot real estate. Radioactive material. The belly of the beast has plenty of uranium and other radioactive elements, all of which release heat as they decay. That decay has significantly slowed the rate at which the Earth is cooling. So what does this mean at the surface? Two things. First, magma being burped up along the ridges, those places like Iceland where the Earth is tearing itself asunder, is pushing the plates in their respective continents apart. Second, what goes on at the other end of those plates, the collision zone, may be equally important. Here, where the heavier plates dive under the lighter ones, yanked downwards by gravity, they haul along their plates back into the oblivion of the mantle. That's what we know. Or what we think we know. But the details of what's going on in the deepest parts of the Earth that drive the engine of plate tectonics, we may never know.
One of the things that happens whenever plates push together, or one may go underneath the other one, our mountains will form. And there are several different types of mountains. We're going to look at 4. There are dome mountains and volcanic mountains and what we call fault block mountains or just block mountains, and then fold mountains. And in the video that you're getting ready to watch, it'll explain a little bit more about each of the different mountain types.
Hi, I'm Emerald Robinson, and in this What Is video, we're going to answer the question, what is a mountain? Defining what a mountain is can be tricky, but a good definition is any landmass higher and steeper than a hill. Many geographers agree that mountains are a minimum of 2,000 feet high and have a slope that's greater than 2 degrees. There are many types of mountains, and they're classified by how they're formed. Volcanic and dome mountains are formed by the molten rock or magma found beneath the Earth's crust. Volcanic mountains are made when erupting magma cools and hardens, forming a cone shape. Dome mountains are made when magma causes the crust to bulge and then subsides, leaving a rounded formation behind. Japan's Mount Fuji is a famous volcanic mountain, while the Adirondacks in the eastern U.S. are well-known dome mountains. Fold mountains form when the plates that make up the Earth's crust collide or pass over the top of one another, causing the crust to wrinkle and fold. The Rocky Mountains in the North American West and Europe's Alps are both fold mountains. Block mountains are made when pressure on giant cracks in the Earth's crust, or faults, cause slabs of rock to tilt upward and sometimes stack on top of one another. America's Sierra Nevada mountains are block mountains. The highest mountain on Earth is Mount Everest in the Asian Himalayan mountains. Its peak reaches 29,029 feet above sea level and is still growing. If you measure a mountain's might by its area, Hawaii's volcanic Mauna Loa is the world's largest at about 75 miles across. Both of these, though, are dwarfed by Olympus Mons on Mars, the solar system's highest and largest mountain, which is over 13 miles high and about 374 miles across.
Just learned in the last slide, or in the last video, volcanoes are a type of mountain. There are different types of volcanoes. We're going to look at what are active and what are dormant. And in the first picture, that is obviously an active volcano. You can see that it is spewing lava. This most likely could be in Hawaii, where several volcanoes are active there constantly. And then the second picture is a dormant volcano. Dormant volcanoes can actually be more dangerous and deadly than active volcanoes when they erupt, and sometimes it is without very little notice. The parts of the volcano can blow off the top and create all kinds of destruction and landslides. And if people are living close enough to that, they can also lead to death. So in the next slide, we're going to take a look, a little bit more information about volcanoes and a little bit more detail about how volcanoes are formed. In this slide, we have an image of the world, and the areas where you see the yellow and the orange and the red are showing where earthquakes most frequently occur, and the magnitude is like a yellow has a lower magnitude, the red has a higher magnitude, all the way up to 9.9. And one of the things you probably have noticed already is the area, the lines of the earthquake correlate with those tectonic plates that we looked at in an earlier slide. And that's because those are where fault lines are. But there are fault lines in other places. For example, if we take a look at the United States, and here this particular map is showing the colored areas. Pink is showing the most hazardous places for earthquakes. And then it goes down to the gray, which there's very little chance of earthquakes. And one of the things I wanted you to notice, of course, if you look over on the western side in California, you can see, we all know that there are earthquakes in Southern California. But surprisingly, if you go back to Missouri and look in the southeastern corner, you'll notice that it is pink there. That is because there is a fault line in southeastern Missouri, and is called the New Madrid Fault Line. So if there were to be an earthquake in that area, it could be quite hazardous. Now, if earthquakes occur out in the ocean, what's going to happen most of the time is, if it's a big enough earthquake, it's going to cause what is called a tsunami. And that's because, like, usually so under the ocean, there is crust. And if there's movement, usually one of the plates slides under the other plate. And that causes a wave to start. Now, if you were out in the ocean, you probably wouldn't even notice it. It might be just a small wave. But that wave continues to build the closer it gets to the land. And this image that you're looking at probably is from Sri Lanka in 2003, I believe, when they had the horrible tsunami that killed thousands of people. And, so that is one of the effects of, if an earthquake happens out in the ocean, it's going to cause a tsunami. In the next slide is a video which is giving you more information about earthquakes.
April 18, 1906, California's San Andreas Fault snaps, shaking San Francisco for nearly 60 terrifying seconds. When the trembling stops, the disaster is only beginning. Gas lines rupture, setting off massive fires. Some 700 people die. Most of the city is reduced to ruins. This trembling of the ground, caused when masses of rock suddenly shift below the Earth's surface, is called an earthquake. Hundreds of little earthquakes shake the planet every day, but most pass unnoticed. They usually occur along the boundaries of the thin plates that cover the Earth, like an eggshell. Driven by the heat deep within the Earth's core, the plates grind against each other along lines called faults. When the plate's motion is blocked, stress builds up. Finally, the fault gives way. The released energy races through the Earth in the form of seismic waves. Scientists record these waves on a device called a seismograph. These zigzag lines show the strength of various seismic waves. Using the lines, scientists grade earthquakes on the Richter scale. For a quake to measure one number higher on the Richter scale, it must release about 30 times as much energy as the number below it. Every year, about 100,000 earthquakes rumble through the ground hard enough for people to feel them. Of these, only about 1,000 are strong enough to damage property. But a powerful earthquake can be devastating. On average, about 10,000 people die each year as a result of earthquakes. The greatest recorded earthquake ever to hit North America measured a massive 9.2. The tremor struck Alaska on March 28, 1964. A camera on board a ship docked in Valdez recorded the draining of the entire harbor as a chasm opened up on the sea floor. There's no stopping the surface of the Earth from changing and moving, so engineers are focusing on ways to create better buildings, highways, and bridges, structures that will remain safe and stay in one piece the next time the Earth begins to shake.
And our last two forces that shape the Earth are weathering and erosion. Let's take a look at weathering first. Weathering takes place as rocks are broken down into progressively smaller pieces by the effects of weather. So think of things like rain and sleet and snow and wind, heavy winds. When this happens, and it takes usually a long time, these pieces do not move to a new location. They simply break down and remain next to one another. So some examples of that would be this rock in the first picture. So what's happened most likely is that water has gotten into a little crack, and over time that water may have even frozen at some point. And when it freezes, it's going to cause the crack to get larger until eventually the rock could break in half. The next picture is the Grand Canyon, and as most of you know, the Grand Canyon was formed by the Colorado River, and the water from the river over time has caused the eroding of the rock and caused it to form the Grand Canyon with some really cool rock formations. Then our last one is erosion. Erosion really is a type of weathering. The difference is that erosion has movement. It moves away. So once again, we have possibly soil or rock that are worn away through 5 different possible agents or actions of wind, water, waves, and gravity. And if you look at the picture, you can see that that is illustrating from waves that have come into the shoreline and caused the erosion not only of the soil, but if you look really closely at that picture, you can see it's even eroded the asphalt from the road. And that's going to happen. Many of you have probably seen where there have been like landslides, maybe even in your backyard. Part of it may have, if it's gotten super rainy or wet, part of it may kind of slide. If you've got a steep hill may slide down. That would be an example of erosion because it's moving. And that a lot of times happens from water, but it can even happen with ice. An example of that would be the Great Lakes. The Great Lakes were actually formed by ice. The ice was there, and over time, the ice melted and moved slowly away. And when it left, there were these craters in the ground from that. And then those are currently the Great Lakes today. So make sure you have your chart all filled out. Remember, if you need to go back or look at anything, feel free to do that, but everything should be filled out. Make sure you have your name on it. And once you are done, you need to turn it in to your teacher.